So those are permutations. Let's now talk about combinations. So combinations define CNR. As you guessed, the C stands for combinations. You might also see NCR, or you might see them written as binomial coefficients, which are written like NR in parentheses, like a fraction, but with no line. So binomial coefficients, we will talk more about tomorrow. And in general, I will prefer this notation because it is more familiar to me, and I think it's more familiar in many contexts. But these all mean the same thing. So define CNR to be number of ways to choose an unordered list which, since we're not allowing repeats, is basically a subset. Of R elements. Ooh, look at that R, incredible. From a set of n elements. As usual, no repeats. Repeats we will come to tomorrow. So, for example, C32 unordered pairs, unordered. Of elements from free element set like this. How many are there? Well, there is 1 and 2. And for permutations, we would consider also 2, 1 to be different. But for combinations, we don't care about the order. So this is the only one of those that we consider. Or we consider them to be the same, that is. You could also have 1, 3, and you could also have 2, 3. But these are all the possibilities. So C32 equals 3. So in general, as I had emphasized a couple of times, CNR is basically the same as PNR, so it's essentially a permutation, except that you are forgetting the order of the elements. And how do we count something like this? This may remind you of the division rule, because this is essentially saying that each element on this side is counted on this side, overcounted a specific number of times. Or maybe that's not obvious, but let's make it a little more clear. How many orderings are there for each subset of R elements? Well, there are PRR of those. This is just the number of ways to order R elements out of a set of R elements. So you're just taking all the elements and ordering them. And this, according to our formula, is R factorial over 0 factorial. So it's just R factorial. If you are not familiar, 0 factorial equals 1. This may seem weird, but it is a definition that is very useful to have, because it makes things work nicely like this. So this is the number of orderings for each subset. So in order to get the number of subsets without worrying about ordering, we just divide by that number. So CNR is PNR divided by PRR, which is R factorial, as we said. And using this formula, this is N factorial divided by R factorial, N minus R factorial. So let's have a concrete example, or another example. How many ways to choose 4 panelists from a pool of 6 potential panelists without choosing a seating? So let's say, this conference that we're organizing is not for another couple of months. So we need to choose who is going to be on this panel, but we're not worried about where they're sitting. That comes later. So without choosing a seating, this just means we're interested in choosing a 4-element subset of this set of 6 elements without caring about order. So this is C6, 4, which is 6 factorial over 4 factorial times 6 minus 4 factorial, which is 2 factorial. So if you're ever faced with evaluating something like this, you will quite possibly figure this rule out on your own very fast. But a good thing to do is to cancel some of your factorials and cancel them as much as you can. So in this case, since 4 is bigger than 2, I'm going to cancel this 4 factorial with this 6 factorial from the 4 down. So I get on the top 6 times 5, and on the bottom, the 2 factorial is the part that's left. So it's just 2. So this is 15 different ways. But let me, it's also true that there will be many problems where you're writing down some answer like this, but maybe you're dealing with a deck of cards, so it's like 52 factorial divided by factorial factorial, and the answer is just going to be just enormous. So you can also, in those cases, you can just leave it in this form. But if it's small enough to compute like this, then may as well write it out. If the answer is 15, better to write 15. So there is a nice concrete example. Here is a useful identity between different combinations. So Cn, R is equal to Cn, n minus R. So this is quite a useful thing when you're working with these numbers, as I think we will probably see examples at some point down the line. And let's prove this. And I'm going to give 2 proofs. Well, okay, I'm going to say one out loud to you right now. The first one is that you can just look at the formula and kind of observe that it is true, because you have the same n on both sides, so you have the same numerator. And replacing r with n minus r just switches the order of these factors, but doesn't really change anything. So from the formula, you can directly see that this is true. But I want to introduce the idea of, so let me write that down. It can be seen from the formula. but you can also give what we call a combinatorial proof. So what is a combinatorial proof? It means that you're proving an identity by thinking about the objects that it represents. Instead of using formulas, you're interpreting these numbers as counting some kinds of things, and you're showing that those kinds of things can be made to agree. So another way of saying this is that you are counting the same things in two different ways. This is a common way to find identities in combinatorics, is you take some element and you count it in one way, that gives the left-hand side of your formula, and you count it in another way, that gives the right-hand side of your formula. And that shows that the formula is true because they're counting the same objects. So let's give a combinatorial proof of this identity. So the left-hand side is choosing a subset of R elements from a set of N elements. And the proof essentially is that this is the same as choosing N minus R elements to form the complement of this subset. And choosing N minus R elements from a set of N is precisely what the right-hand side is counting. So that completes the proof. So essentially we're just saying that it is the same to choose R elements to include in your subset as it is to choose N minus R elements to exclude from the subset. So these are essentially both counting subsets of R elements from a set with N elements. So they must be equal. And we will see more combinatorial proofs in the days to come. And it's nice because somehow it's more satisfying than giving a proof from the formula. Because a proof from the formula is fair enough, works very well. But a combinatorial proof somehow feels like it's giving you more insight into why these things are the same or what's going on.